Transport through neutral membranes is vitally important for all biological systems because of several things. But here are the kind of things we're gonna cover as we go through this: membranes, osmotic pressure, clinical examples, volume transport, solute transport, an artificial kidney, how that looks, countercurrent transport, and pores. Um, the reason this is so vital to biological systems is that membranes keep things in, right? You know, the cells have a membrane about 7 to 10 nanometers thick. Everything inside of a cell, every identifiable piece inside of a cell has a membrane around it that's a few nanometers thick. And these membranes have to be permeable or semi-permeable. If they're impermeable, then, um, whatever the object that's inside of it is completely cut off. And so nutrients can't flow and other things can't flow. So impermeable is I put it on the list, but it's not a biological thing, right? Impermeable membranes aren't very useful unless you're trying to um, unless you're trying to close off a cyst of some sort. Um, Permeants are the things that go through the membrane. Most of everything we're talking about here is in water. And so as we go through this, the background, like in chapter 3, the background of this is everything's in water. Um, and the human body is lots and lots of water. Solutes are the things that dissolve in water, of course. Diffusion there are two major ways things move through membranes. One is diffusion, where that's more like up here, where the particles that can go through, they're small enough to go through a pore or through a membrane, um, diffuse through, right? They're not shoved through by the solute, but then there's solute drag. So if the water is going from one place to another, the solutes in it are going from one place to another. And then down here, this is pure diffusion. Um, the water and the solute both diffuse through the membrane and slowly make their way to the other side. Um, so let's take a look at the ideal gas law. And you're thinking, why are we looking at the ideal gas law? Because we're talking about water all over the place. There's a reason for this. So let's first talk about the ideal gas law. It's a little easier to picture in the context of the ideal gas law. So I've got P1 V1, and P1 V equals N1 kBT. All right, or if for the chemist, you like to write it in terms of moles. Um, and here's the concentration in terms of particles per cubic meter. Here's the moles. So, and that should be an R. Ha, there we go. Um, so this ideal gas law, let's consider when we stick a membrane, a barrier here, a semi-permeable membrane between the two halves. Well, at first, there's nothing different, right? All we've done was taken this volume and we divided it in two. But now we have two sides we can talk about, and we can begin doing stuff to one side that we don't do to the other. In particular, if over here, where we're at now, we've stuck a new species, a new atom, a new molecule, whatever, into one side here. Once we've done that, and in particular here, we've stuck one in that can't go through the membrane. So what's happened? All right, the pressure's gone up over here. What's going to happen over here? Well, the answer is actually nothing, right? Um, the fact that the pressure is now higher over here does not drive the first species to the other side. It's not that the pressures have to balance across the membrane. The partial pressures have to balance, right? So the partial pressure due to P1 is going to just stay the same. All right, so here we are. The important thing, the um, important thing to remember is it's not from higher pressure to lower pressure. It's higher partial pressure to lower partial pressure. Right? So we're talking about moving due to partial pressure. And in fact, you can take a balloon, a latex balloon, which is permeable to air, otherwise they wouldn't deflate, right? You can take a latex balloon and you can blow it up with a large molecule gas that will not pass through the latex. So now you've got a balloon that's blown up and it's just P2. Outside the balloon, there's air. Well, even though the pressure inside the balloon is above atmosphere or is at atmosphere, air is going to be leaking into the balloon because the partial pressure inside the balloon is below the atmospheric pressure of the air outside the balloon. And this will happen until the balloon pops. Right? Air will keep going into the balloon because of the partial pressure. Doesn't matter that the pressure inside the balloon is already at atmosphere. That species there doesn't matter when it comes to calculating the partial pressure. Um, and here, the other thing about osmotic pressure, it's usually not, we usually think of it as a thing that's going through, but osmotic pressure is actually due to the stuff that's not going through. All right, so osmotic pressure in this case is the pressure due to the species that can't go through. All right, pressure due to the species that can't go through. And remember, C2 is just N2 over V, right? It's just the number of particles per unit volume. So osmotic pressure in an ideal gas, right? All flow species capacity may be from the region of higher chemical potential to lower chemical potential. That gives us a little bit more to think about, but higher chemical potential to lower chemical potential, and that's going to be the flow of particles. So let's start looking at this in a fluid. Let's start talking about the chemical potential of water across a membrane. All right, the chemical potential of water, pressure minus kBT delta CS, concentration of the solute, over the concentration of the water. So there's no movement of water when the pressure minus the osmotic pressure on one side. So osmotic pressure is P2, pressure is P is the total pressure, and P prime is the pressure over here. So there's no movement of water when this basically ignore the things that can't go through the membrane. All right, P2 can't go through the membrane. When the level between the things that can go through the membrane is the same on each side, then we're good. All right. And so this driving pressure, this difference is what we're going to call, is what's driving water through. And there's no movement when the driving pressure from both sides is the same. So even if, let's say we had oh, we'll get there, never mind. Right? Or when the chemical potential for the water is the same on both sides, there's no movement. If we increase the concentration of the solute, we increase the osmotic pressure, right? So for an ideal solution, this pressure is just C kBT or CRT. And this is just the osmotic pressure again is due to all the things that can't go through. So if we add in more stuff that can't go through, clearly the osmotic pressure goes up. All right. And so a few review of terms that you're going to run into again and again in the text: osmol, mole of solute particles; osmolality, number of osmoles per kilogram of solvent; and osmolarity, number of osmoles per liter of solution. All right, we went over these in chapter 3, but again, just a review here. All right, and that's it for this segment, and there will be another segment coming.